In this video, we'll talk about the lecture notes for 1.7, Heat Conduction in Higher Dimensions. For this video, we'll look at heat conduction in R3. We're going to start by looking at some body omega. Omega is a region in R3, somewhere where heat is flowing. We'll let U be the temperature at a given point in omega at a specific time t. And we'll let B be an arbitrary sphere which is contained inside the region omega. In particular, we're assuming that omega is a region that has spheres that are contained entirely within it. We will apply the energy balance principle to B, and we will derive a local version of it, and that will give us our next conservation law. The energy balance principle says that the rate of change of heat energy in B is equal to the rate heat flows into B across its boundary, plus the rate heat is generated in B by sources. Or, if it's negative, then it's the rate heat is destroyed in B by sinks. We'll make some simplifying assumptions. We'll assume that omega has constant density ρ, and omega has a constant specific heat, C. The specific heat is the amount of energy required to increase the temperature of 1 unit mass by 1 degree. These assumptions will make it easier for us to do our computations. We're going to compute each of these, 1, 2, and 3, separately, and then we'll put them all together as our energy balance principle. Let's start with 1, the rate of change of the heat energy in B. Well, the first thing to do is look at the heat energy in B at a specific time t. And once you have the heat energy in B, if you want to compute the rate of change of it, you simply compute the derivative. So the heat energy in B at a specific time t is given by this integral here. This is the integral over B of C times rho times U at x, y, z, comma t. This is a volume integral. Where does this come from? Well, if you look at a small cube about a fixed point, so suppose that x, y, z is a given point. Suppose that it's this point right there. And if you look at a small cube about it, where the dimensions of the cube are delta x by delta y by delta z, we're imagining that this is an incredibly small cube, then the heat energy in that small cube is given by C times rho times U at x, y, z, comma t times delta x, delta y, delta z. We usually just call that delta V. This is a small unit of volume. If you multiply this delta V by the density, that's going to give you the mass. So when you multiply it by the specific heat, C, and multiply that by the temperature at that point U, or that point, the temperature U at that point, x, y, z, comma t, that's going to give you the heat energy in that small cube, at least approximately. We imagine this cube is very tiny. As you compute the limit as delta x, delta y, delta z go to 0, then you end up with an infinitesimal unit, and you add all those together, so to speak, in terms of an integral, and that gives you the heat energy over the sphere, or inside the sphere as well. We're thinking of this as a solid sphere, or at least as a sphere on the boundary and its interior together. Not necessarily solid in the sense that it's a solid physical object, but we're considering B to be a sphere on the and also its interior. So what we have is we have the heat energy. This is a function of t. T, of course, is time. X, Y, Z, those are our coordinates in three-dimensional space. So we're looking at a small cube here about a point at a fixed time. So time is fixed. So when you compute this integral, you're going to get a t in it. So the heat energy depends on time. So it's a function of time. If you want to find the rate of change of this heat energy, then we compute the derivative, and that gives us the rate of change. that's 1. That gives us 1. Let's skip 2 for a moment and we'll go to 3 because that's probably the easiest one. If the heat source is given by some function f, then 3, which is, if we just go back, 3 is the rate heat is generated in B by the sources. All we have to do to compute that is simply integrate it over B. Again, this is a volume integral. So in our small cube from above, so we have this point x, y, z right there, and we have the small cube of dimensions delta x, delta y by delta z. The heat generates, assuming that f is a source, the heat is generated in that cube at a rate approximately equal to f times delta v. So again, delta x times delta y times delta v, that's delta z, that's delta v. This is our small cube. So f gives you the heat generated at a point, so if you multiply it by the volume, then you get the heat generated in that cube. Now this is approximate. We're imagining that it's constant throughout that small cube. So that's an approximation, but the approximation gets better and better as you compute the limit as delta x, delta y, and delta z all go to 0. Note that the units of F must be energy per unit volume per unit time in order for this to actually give you the right quantity, because we want this to be the rate at which this is happening. Let's go back to 2. So for 2, let's just scroll back. For 2, we want to compute the rate heat flows into B across its boundary. So for that, we're going to need a normal vector n. So let's say that we have one. Let's look at this little picture right here. This is a small surface area element, a small element of the surface, and it has surface area delta A, which is just some small surface area. N is going to be our normal vector. We're assuming that this surface is oriented by n, and n is the outward pointing normal vector. And we can do that because this is a sphere. We know that spheres can be oriented. So let phi be the heat flux vector. That's this thing right here. This gives the direction and magnitude of heat flow at a specific point at a specific time. So phi is giving you the magnitude and direction of heat flow, but we're interested in the rate that heat is flowing across the small piece of our surface. So in order to measure that, we compute the dot product. So we're looking at phi dot n, where again n is a normal outward pointing, n is an outward pointing normal vector. This is giving us the heat that's flowing outside of our region. So the net rate of change across the boundary, which we're calling boundary B here, this is our 2, this is our object 2, it's equal to the opposite of the integral over the boundary of phi dot n. So this is measuring, so there's a minus sign here for a reason. This integral is measuring the energy that's flowing out. So phi dot n, well, times delta A times our surface area element. This is positive when heat is flowing outward because n is pointing outward. Our surface here is oriented by n, and n is an outward pointing normal vector. So if you look at the dot product of phi with n, that's measuring how it's flowing out. We want to say that it's positive if it's flowing in. 2 is the rate of heat flowing into B. Since this integral is positive when it's flowing out, we need to put a minus sign in front. And that's why that minus sign is there, just to make sure that the direction is, I don't want to say right, but we just want to make sure that that we get a positive value when it's going in, because we're trying to determine the rate at which energy is flowing into the object. So we want a positive value. We want a positive value for what's flowing in. The integral gives you positive value if it's coming out. So that's why we have that minus sign. Okay, so now let's put all that together. So we have 1 is equal to 2 plus 3. So now we have our energy balance principle in terms of integrals. At this point, we're going to use the divergence theorem on that second integral, right there. So the divergence theorem tells us that the integral over the boundary of B of phi dot n dA is equal to the integral over B of the divergence of phi dV. So the divergence theorem tells us how to convert a surface integral into a volume integral, and that's what we're doing here. So here we're making some assumptions. We're assuming that phi is continuous on the closed region B. So B with a bar over it I'm using to mean the closure, the topological closure of B, which is B together with its boundary. So that's just another way of writing that. Oh, I don't need to put this here. I just need this, the boundary of B. There we are. So we're assuming that phi is continuous on this closure and it's differentiable inside of B. All right, so our energy balance principle then can be written in the following way. So we have the rate of change, d by dt, of the integral over B of c rho u dV. So here we're going to apply Leibniz's rule for integrals again, and we just take that derivative and bring it into the u. Now, c and rho are constant, so we don't need to worry about differentiating them with respect to t. So we just compute the derivative of u, and that gives us the integral over b of c rho u sub t, or the derivative of u with respect to t. Now what about on the right? On the right we have two integrals over b that are volume integrals, so we just combine them. So we have minus the divergence of phi plus f. Now we have two integrals again. We have an integral on the left, which is an integral of b with respect to v, so it's a volume integral over b, and on the right we have a volume integral over b. So if we just put all of those on the same side, then on the right we have 0, and on the left we have one integral over, which is a volume integral over b. But this has to be 0 for any ball. The b was completely arbitrary. It was just any ball of any size. The only restriction was that it needed to be an omega. So if this is true, the only way that this can be true is if the integrand itself was 0. So that means the integrand is 0. So that's what we've written here. So c rho partial of u with respect to t plus the divergence of phi minus f is equal to 0. And then just for fun, we're going to add f to the other side, and that gives us this statement. And this is our conservation law, or at least a local form of it. The next thing we need is Fourier's heat conduction law. So the heat conduction law says that the flux is equal to minus k, where k is some positive constant called the thermal conductivity, times the divergence of u, the gradient of u. That's the gradient of u. Fourier's law says that heat flows down, we don't want to cross it out, we want to underline it. Fourier's law says that heat flows down the gradient. So let's take a look at what's going on here. So recall from your calculus class that the gradient points in the direction of maximal increase, and the opposite of the gradient, if you change the direction, that points in the direction of maximal decrease. So what Fourier's law is telling us is that the flux, which gives us the size, the flux vector gives us the size and the direction of the flow, is equal to minus k times the gradient of u. So the flux is equal to some constant times minus the gradient of u. So in other words, the direction of the flux is in the direction of maximal decrease of u. So that's what we mean when we say it flows down the gradient. It's going in the direction of maximal decrease. K is some constant of proportionality called the thermal conductivity. This is Fourier's heat conduction law. This is the R3 equivalent of Fick's law that we saw earlier. So we have a conservation law and we have Fourier's law. And we're going to combine these. Basically, we're going to take this phi and plug it into there. Now, what we need to do, of course, is we need to compute the divergence of phi. The divergence of phi is equal to the divergence of the gradient of u. So we just plug that into there, and that gives us this. Now the divergence of the gradient has another name. That's called the Laplacian of u. And it's usually written in one of two ways. It's either written as this delta u, or it's written as this symbol, which is the gradient squared, I suppose you could call it. This is the Laplacian of u. These are two different notations for the same thing, but what it means is it means the divergence of the gradient. Now we can actually compute the divergence of the gradient, and of course it's the second partial of u with respect to x plus the second partial of u with respect to y plus the second partial of u with respect to z. So this is the Laplacian. So if we just rewrite our conservation law using Fourier's law, we end up with c rho times the partial of u with respect to t minus k times the Laplacian of u is equal to f. So what I'm going to do now is I'm going to just divide by c times rho, and that gives us this equation here. So I've just divided by c times rho. Now this constant, capital K divided by c times rho, we call that little k, lowercase k. This is the diffusivity. And we just combine all of our constants into there, and then we just call that lowercase k. And that gives us our conservation law. The partial derivative of u with respect to t minus lowercase k times the Laplacian of u is equal to 1 over c rho times f. This rho started to look like a p, but that's a rho. If the source term f and the boundary conditions on omega are independent of time, then we expect omega to eventually reach an equilibrium temperature that is independent of time. In this context, we have the partial derivative of u with respect to t equals 0 if we're in an equilibrium temperature that's independent of time. So this is called a steady state. So if we're in a steady state which doesn't depend on time, then this partial derivative is 0. So then we just end up with what's called Poisson's equation. Minus k times the Laplacian of u is equal to 1 over c rho times f. This is Poisson's equation. If there are no sources, then that means that f is equal to 0, and then this simplifies to what's known as Laplace's equation, which is just that the Laplacian of u is equal to 0. Since Laplace's equation does not contain time, we don't expect to need an initial condition. We do require some form of boundary conditions, however. An initial condition wouldn't really apply in a situation where the equation itself doesn't contain time. But we do need boundary conditions. So there are two main types of different boundary conditions. The first one is when temperature along the boundary is given as some prescribed function. This is known as a Dirichlet condition. The other type of boundary condition that you might know is known as a Neumann condition, and that's when you're given the heat flux on the boundary. So the heat flux along the boundary is equal to some prescribed function. Now this occurs quite a lot, and so there's a special notation which is invented for this expression here, this gradient of u dot n. This shows up quite commonly, so it's given this notation here, du dn. It's called the normal derivative. So du dn is equal to the gradient of u dot the normal vector n. This is supposed to be an n here. This is the definition, and it's basically a directional derivative. It's computing the derivative in the normal direction. That's why it's called the normal derivative.